So next question, why does that Riemann sum in the last problem, why it is between the corresponding lower sum and upper sum? Based on this fact, why can you conclude that the limit of the Riemann is exactly equal to that integral? Well, we're just going to worry about the integral part of this question. When you look at that summation, what did we have? T equals 0 to 100 of v of t dt. If I put a limit out in front of this, and it could be either dt approaching 0. Let's do that since we have a dt in there. In other words, I'm saying that the width of my rectangles is getting teeny, teeny, tiny. Okay? Do you remember, which some of you might not because you missed this on your test, the definition of our definite integral that had this symbolism in it? Remember that we had one that looked like this, and then we had one that had h approaches infinity. Okay? When you put a limit out in front of that summation, that makes it an integral, because that's what this is the definition of. It's a definite integral. Definite means we have bounds, so we're going from 0 to 100 of v of t dt. Now, the next one wants you to actually evaluate this problem. Oh, sorry. Next one wants you to actually evaluate that. So let's go back and put our function back in here. 3,000 plus 18t to the 1/4, or 1.4. Now, this is fundamental theorem of calculus. So Mitch, help me out here. Antiderivative of 3,000 is, you can do it. We're doing this. We worked on this morning, remember? What's the antiderivative of 3,000? What did he say? 3,000x, and in this case we have a t, so we'll put t in there. We're not there yet, and we aren't going to need a plus c because we have 0 to 100 there. If we didn't have those numbers, we'd have to put plus c. On the next one, what am I going to do to find the t to the 2.4 and divide by 2.4? And we're going to go from 0 to 100. So go ahead and plug in 100 and 0. It looks like if I plug 0 into this, I'm going to get 0 out of it. So basically you need to plug 100 in and see what you get. Okay, so let's plug in 100. Divided by 2.4. This whole thing back here is 0, right? Alright, so you can either type it in times 100 plus, what was that? Tangentially was all I heard. Oh, if the Earth would stop spinning, you would fly off of it tangentially. Okay, gotcha. Is that what you guys got? Now, do you remember? No? Well, if you didn't do it, of course you didn't get that. Do you remember the other way that we can come up with this answer on our calculator? Because, like Margaret, you weren't here. I showed them how to check. What do? We go math 9, put in your equation. So, and remember that you want whatever you're taking the antiderivative of. So we go back to 3,000 plus 18x to the 1.4, comma, x, and then your bounds, comma, 100. All right, Corey. And the calculator obviously has to think, but it does come up with the same answer. So 2 possible ways. I'll make this a little bigger so you can see what we did there. 2 possible ways to come up with your antiderivative there. You would still need to show me your work, but you can double check with that. Questions there? Margaret, does your calculator work okay? Did you try that on your, okay, and you got it to work? Good deal. Any questions there? Next page. Number 7. In order to orbit, the spaceship must be going at least 26,000 feet per second, about 17,500 miles per hour. So there's your orbit speed, Megan. To the nearest second, at what time is it going this fast? We want our velocity, yeah, Peter, that would be an option to trace. We want our velocity, whoops, not 17,000, that's the miles per hour, to be 26,000, right? So Peter says, we can't trace, but we could do it. We could come close with tracing, but we couldn't be exact. We can do an intersection. So if we put in 3,000 plus 18x raised to the 1.4, and we would have to put in our other equation, 26,000. Is there a way to do that? How? Yes, there is a way to do that just using the equation. I can show you that next if you want me to. We'll want to go from 0. I've got the window here. 200 is what you will cover it well. And then we've got to go for, I'm going to set my x scale at 0. And for my y's, I've got to go above 26,000. 30,000, that sounds good. And I'm going to set, do you guys know what setting your scale to 0 does? Yeah, you don't have a fat axis, because if you leave your scales too small, it'll put way too many marks. Fat axis. You all haven't heard fat axis before? It's okay. All right, there's the velocity, and there is the line where it's 26,000. We do a calculate, intersect, enter. You don't always, some people just go ahead and hit enter. I like to get a little closer just to help old T.I. Joe out. Uh-oh. Okay. He does. He has a name. I'm okay. I still got a little time. Let me drag this over and I'll stop. Julia's going to think I'm crazy. That's okay. Julia knows I'm crazy, don't you, Julia?